We've spent a lot of time talking about supervised machine learning techniques and the regression and classification settings. We're now going to make a big pivot into the world of unsupervised learning. In this two-part video series, we'll discuss one unsupervised technique, hierarchical clustering. In general, we do unsupervised learning when we have some features or variables x, but no particular outcome or response variable y. Mainly, we're not trying to predict or classify anything. We're simply trying to understand the structure of our data with respect to x. Consider some examples. First, a music platform might use features such as tempo x1 and valence or happiness x2 to identify similar groups of songs for a playlist. They aren't trying to predict anything about a song, just to identify similarities that might be used to create, again, playlists or stations. Relatedly, a music platform might use listeners' previous listening habits, X, to indicate or identify groups of similar listeners. They're not trying to predict anything about listeners here, but just trying to understand different types of listening behavior. Finally, a scientist might use measures of penguins' bill lengths, X1, bill depths, X2, and body masses, X3, to determine how many different penguin species there might be. Again, we're not trying to predict anything here, just trying to understand the underlying structure of penguins. We'll continue pursuing this question throughout the video. That is, we'll use measures of bill depth and bill length in addition to body mass to help identify possible penguin species. The plot here considers these three metrics among a sample of 50 penguins. For ease of comparison, on the axes, each of these features has been standardized to the same scale, centered at 0 with a standard deviation of 1. Further, the numbers inside the plot represent the labels for our 50 different penguins. And we can start to pick out some patterns among these penguins. First, there appears to be a group of penguins that have high mass and length, and another with smaller masses and varying lengths. Another way to examine this same data is with a heat map. Here, each column represents one of the three penguin features, bill depth, bill length, and body mass, and each row represents the scale of these three measurements for a single penguin. These rows are labeled with the penguin's ID numbers at right. The pinker the color, the greater the measurement. The bluer or more aqua the color, the smaller the measurement. As is, it's not easy to pick out any patterns in the heat map. It just looks like a jumble of colors. But we can reorganize the rows so that more similar penguins are closer together in the heat map. After doing this, some patterns start to emerge. First, we notice a group of penguins that have smaller bill depths and larger bill lengths and body masses. Among the other group of penguins, the middle column of the heat map indicates that we might further divide these penguins according to differing lengths. Thus, though both groups of penguins have larger bill depths and smaller body masses, the first group has larger bill lengths, whereas the second has smaller bill lengths. Of course, we can do better than guesstimating the structure of our penguins. The goal of clustering algorithms is to provide a formal mechanism for examining and discovering structure among the cases or subjects in our data. Two common clustering algorithms are hierarchical clustering and k-means clustering. We'll focus on the former here. To explore how this algorithm works, we'll start by clustering just 6 penguins based on only 2 features, mass and bill depth. That is, hierarchical clustering seeks to identify similar clusters of penguins. In the first step, we calculate the Euclidean distance between each pair of penguins. That is, how similar or dissimilar each penguin is from the others. For example, we calculate the distance between penguin 1 and the other 5 penguins. Then the distance between penguin 2 and the other penguins, and so on. Among all of these, penguins 3 and 4 are the most similar pair. The distance between them is so small that it's barely visible here. We then combine these two penguins into a single cluster, the distance between them being 0.08, a number I calculated in the background. We communicate this clustering in a dendrogram. The branching here indicates that our first cluster combines penguins 3 and 4, and the height of this branch indicates the 0.08 distance between them. So now that we have our first cluster, we can move on to step 2, identifying the next cluster. Again, we look for the most similar pair of the 5 remaining clusters. Since penguins 1, 2, 5, and 6 are still in clusters alone, we can examine the distance between each pair of these penguins as usual. But what do we do with a cluster containing both penguins 3 and 4? For example, how far is penguin 6 from this cluster? There are multiple ways that we might answer this question. Consider 2 generic clusters, one containing 3 cases and the other containing 2. Pause to think about how you might calculate the distance between cluster 1 and cluster 2. It turns out that there are 4 common strategies. First, complete linkage defines the distance between 2 clusters to be the maximum distance between any case in cluster 1 and any case in cluster 2. Here, that maximum distance is represented by the red dashed line. Similarly, single linkage defines the distance between 2 clusters to be the minimum distance between any pair of cases. Yet another strategy is to examine the distance between every pair of cases in the 2 clusters and then calculate their average. Finally, centroid linkage identifies the centroids or centers of each cluster, represented here by the red dots, and then calculates the distance between these centroids. You'll get to play around with all these strategies in another context, but for the purposes of this video, we'll use one of the most common approaches, complete linkage. Using the complete linkage approach, we can now define the distance between any single penguin and the cluster of penguins 3 and 4. For example, penguin 5 down at the bottom is slightly farther from penguin 4 than from penguin 3. Thus, the distance between penguin 5 and the cluster of penguins 3 and 4 is simply the distance between penguins 5 and 4, represented by the red line there. Similarly, penguin 6 is farther from penguin 4 than from penguin 3. Ditto for penguins 1 and 2. They're both further from penguin 4 than from penguin 3. We've now measured the distance between every pair of our 5 clusters. Among these, the smallest is the distance between penguins 5 and 6. That is, these are the most similar. Thus, we cluster these penguins 5 and 6 together. The height of this new branch is 0.27, the standardized Euclidean distance between these 2 penguins. We now have 4 clusters, penguin 1, penguin 2, the cluster of penguins 3 and 4, and the cluster of penguins 5 and 6. And we're going to keep going until we have only 1 cluster. To this end, we again examine the distance between each pair of clusters. First, consider the distance between our 2 clusters circled in red. Using complete linkage, the distance between these 2 is the maximum distance between any pair of penguins in the cluster. Here, that max distance is between penguins 4 and 6. Next, we can examine how far penguin 1 is from penguin 2, the cluster of penguins 3 and 4, and the cluster of penguins 5 and 6, within which penguin 1 is slightly farther from penguin 5. Similarly, we can examine how far penguin 2 is from the other 2 clusters. Finally, examining all of the distances here, notice that our 2 clusters in the bottom right corner are the most similar to each other. Thus, we fuse these 2 clusters together into a single branch or even bigger cluster. The height of this branch is 0.59, defined by the distance between the 2 clusters. Here, the distance of 0.49 between penguins 4 and 6. We now have 3 clusters, penguin 1, penguin 2, and the big cluster of penguins 3, 4, 5, and 6. Among these, we can examine the distance between penguins 1 and 2, then the distance between penguin 1 and a big cluster, here defined by the distance between penguins 1 and 5, since 5 is the farthest from 1. Finally, the distance between penguin 2 and the big cluster, here defined by the distance between penguins 2 and 6, since 6 here is farthest from 2. The most similar pair among these 3 clusters includes penguin 1 and 2 with a distance of 1.45. We're now down to 2 clusters, the 2 penguin cluster up top and the 4 penguin cluster down at the bottom. And the maximum distance between any pair of penguins in these 2 clusters is that between penguins 2 and 6, with a distance of 3.27. And we're done building our dendrogram. To recap, we started with 6 one-penguin clusters. We first fused together penguins 3 and 4, followed by penguins 5 and 6, then fused these 2 clusters into a bigger cluster. We then fused together penguins 1 and 2, leaving 2 final clusters, which we then fused into one big cluster. In part 2 of this video series, we'll formalize the hierarchical clustering algorithm that we used here.